Hello everyone, my name is Fadi Ketula, and today my team and I will be presenting an efficient solution for the depletion crisis of rock phosphate.
Phosphorus is an essential and indispensable macronutrient for all living organisms that is responsible in building RNA, DNA, as well as structural cellular components. Even though it is a finite resource, it is a non-negotiable requirement for life. Today, nearly 90% of the Earth's phosphorus reserves are being used in the global food supply chain, and the majority of it is being used in commercial fertilizers to boost crop yields. Farmers in Ontario apply these rock phosphate-based fertilizers to roughly 70% of the cropland available in the province. As global populations and the need for greater food production increases, so does the demand on this non-renewable monopolized resource. The Ontario agriculture industry is a major player in supplying food to millions of Canadians and global populations. However, the farmers' reliance on rock phosphate-based fertilizers is not sustainable and contributes to many environmental, economic, and social issues. The team at VASAF Inc. has designed a solution that utilizes alternative sources of phosphate with improved nutrient management practices to help Ontario farmers reduce their reliance on rock phosphate-based fertilizers while maintaining successful crop yield. Improvements to the mining and extraction process are out of scope for this project, and in simplest terms, we have focused on the investigation of an alternative and sustainable form of phosphate, as well as means of more efficient fertilizer application.
The constraints and criteria for this design had to be clearly identified. The constraints included that any applied materials such as ASM, NASM, or commercial fertilizers must be approved by their respective provincial regulations for applications on cropland. The design must also meet plant phosphorus nutrient requirement to ensure successful crop production. Any design manure handling systems or precision agricultural equipment must follow the Farm Implements Act. And lastly, the design must ensure operator safety and cannot cause any adverse environmental impacts not already present. The criteria for this design included that the capital, maintenance, and recurring purchasing costs should be minimized as much as possible to remain affordable for farmers. The phosphate runoff potential should be minimized to prevent adverse environmental impacts. The simplicity and accessibility of the design should be maximized to ensure operability on site by the client. The startup time of this design should be minimized to prevent disruptions to the client's schedule as well as potential profit. And lastly, the design life of the product should be maximized. Once the problem was identified and the constraints and criteria were clearly defined, the team conducted several meetings to discuss and brainstorm potential design solutions to the problem. The team focused on making all the alternative designs different from each other, as well as making them creative, innovative, and diverse to the solutions currently being used worldwide. After evaluating the potential ideas, 4 design solutions were chosen for further analysis, which were then split amongst the team members equally for research and implementation. The first alternative focused on using agricultural source materials, specifically animal manures, to recover phosphates through a process called hydrothermal carbonization, which saves energy but is not feasible. The second alternative focused on creating an alternative fertilizer to be used on crops using high-rate algal ponds from secondary wastewater treatment plants to create microalgae biomass, which will increase the absorption of phosphorus in soil but will use a large percent of rock phosphate in the process. Alternative 3 proposed the use of field-based sensors to obtain signals from the soil when the sensor detector is close and indicate where phosphorus levels are high prior to fertilization through soil mapping, which would allow for faster and more accurate results but will disrupt and change the farmer's existing habitual patterns. Lastly, Alternative 4 composed of 2 combined technologies: a runoff recycling system, which includes the collection, storage, and injection of phosphorus-rich runoff water, and the use of phosphorus solubilizing microorganisms, which are bacteria and fungi that are capable of hydrolyzing both organic and inorganic insoluble phosphorus into soluble forms that plants can access and utilize. After applying the decision matrix, Alternative 4 was chosen to be our optimal design. Several tools were used to aid in the creation of the optimal design. Mind maps were used to determine different aspects of the problem and specific areas the team could target in order to tackle the depletion of rock phosphate. A decision matrix and sensitivity analysis were both conducted to compare each of the alternative design solutions and to pick the optimal design alternative. The U of G library was used for extensive research on each potential solution. Microsoft Excel was used for calculations and charts that allowed us to compare costs and phosphorus levels of our proposed solutions. AutoCAD was used to sketch potential designs and provide drawings to the client. AgriSuite was used to determine the optimal method to store, treat, and use fertilizers and to ensure that crops are receiving the correct amount of phosphorus. And lastly, OneDrive and Facebook Messenger were used as a communication means between our group members.
For our final design, like Ahmed said, we chose the runoff recycling idea. This idea is composed of 3 main stages in order to maximize the amount of crop available phosphorus. These 3 stages include seeding the field with phosphorus solubilizing microorganisms alongside an initial round of fertilizer application, followed by collecting runoff from the site within a pond and reapplication of this runoff water back onto the field. To develop our design idea, we chose a sample test site located in Chatham, Kent that has a history of growing soybeans. To increase the soybean yield from an estimated provincial average of 47 bushels per acre to our goal of 65 bushels per acre, we found that 30.2 kilograms per hectare of phosphorus would need to be applied. Using collected data on the water balance and soil conditions of the area, we determined that in order to meet this constraint, 970 meters cubed of runoff would need to be recycled. The main component of our design is the direction and collection of surface runoff into a pond located on the downslope end of the property. The pond, which is trapezoidal in shape, was designed to follow both the MOE and OMAFRA pond guidelines. The pond will contain a permanent pool to settle out particles and ensure water quality. With this pool, as well as the volume to retain runoff and a freeboard, the pond will be 3.3 meters deep and have a surface area of 988 meters squared. In the case of a very large storm event, excess water will be directed using a conduit to the local service ditch. Water from the pond will be removed using a submerged intake and a centrifugal pump. The intake, which is located in a barred concrete structure, has been designed to ensure stability and optimal water quality from the pool. In terms of the pump, a model from Gould's water technology was selected. It is capable of operating at both the minimum and maximum water levels of the pond at efficiencies of 65 and 69% respectively. The pump will deliver water to the chosen liquid manure spreader, where it will take approximately 25 trips to apply all the dissolved phosphorus. This spreader was selected as it directly applies fluid to the crop root, which minimizes any potential contamination on the crop and also avoids further environmental loss of phosphorus. To encourage the maximum uptake of phosphorus by the crop, our design also employs the product called Jumpstart, which includes the PSM penicillin belayii. PSMs convert insoluble phosphorus already present in the soil into soluble forms that soybeans can use to grow. In our design, the farmer will coat their soybean seeds prior to planting by mixing the inoculant powder with a pre-described amount of water in a small cement mixer. The seeds will be spread using the same planting equipment already employed on site. With legacy levels of phosphorus in Ontarian soils, this product will promote the use of a previously unattainable phosphorus resource.
The functionality of the proposed design was determined by properly modeling the critical design parameters and selecting optimal operating conditions to ensure high yield efficiency. The pond is designed for a 2-hour storm event where 90% of the runoff from the farm will be collected. A trapezoidal shape was chosen as this is the most common shape used to design a stormwater pond. The intake was designed so the pump operates at both minimum and maximum pond water depths. This will help to reapply the collected water during small and large rainfall events. Previous studies have proven that using PSMs will increase crop yield and improve phosphorus intake. Therefore, utilizing this design will decrease fertilizer use by approximately 29% while increasing yield by 39%. This meets our project goal of reducing farmers' reliance on phosphate fertilizers while maintaining beneficial crop yields. In terms of safety standards, to ensure the pond is functioning properly and is able to collect the effective storage volume, bathymetric and sediment testing surveys will be completed every 5-10 years. When constructing the collection ponds, Occupational Health and Safety Act and the Ontario Regulation 213/91 for construction projects will be followed. The pump was designed to work with a full-flowing water supply so a steady pressure is maintained to prevent cavitation. The AgriSuite crop calculator was used to ensure soybeans are receiving the required amounts of phosphorus. The Jumpstart inoculant used for this design is approved and registered under the Fertilizers Act. Along with these safety guidelines, the constraints and criteria outlined previously were also followed. There are a few risks and uncertainties associated with the proposed design. Based on the slope of the site, it is uncertain that 100% of the phosphorus will go to the pond. Therefore, it was estimated that only 80% will be collected and reapplied. The application rate of the spreader is based on the ideal operating conditions. Therefore, uncertainties can arise if the application rate increases or decreases, as the time to empty the tank and apply fertilizer may vary. As the pond was designed for a 2-hour storm, a larger storm can result in an overflow. In this case, the water is assumed to be directed by an overflow conduit to the local pre-existing ditch at the site. This would result in a loss of total phosphorus collected. As studies have been completed proving PSMs do in fact improve crop yield, further studies need to be completed to assess the success of using the inoculant product Jumpstart containing penicillin billi on soybean crops in Ontario.
Now, with the implementation of our design, we made sure to have some environmental, economical, as well as social benefits. Starting with the environmental, we have the reduction of the risk of eutrophication for the ponds nearby. Now, this is because the phosphorus and the runoff is being contained within site. Now, secondly, we have the reduction in the toxicity of the soil since more phosphorus will be available to the crop. And finally, we have the potential reduction in mining emissions. And moving on to the social and economic benefit, we have the reduction in application, and this was estimated to be 29%. Therefore, less rock phosphate is required for having the same yield. And we also managed to increase the crop yield by applying the Jumpstart, which is made out of PSMs. Now, as for the cost analysis for this project, we have divided it into 3 sections: pre-construction, during, and post-construction. For the pre-construction, this would basically include just the research and development we had to do to come up with the solution, and this would equate to around $21,000. Now, moving on to the during construction, this included the excavation, the equipment, along with some installation. Now, in addition, this also included the corporate fees and the contingency fee. This also includes the project management for the duration of the project, which is 3 months. Now, this would equate a grand total of $61,000, including the pre-construction. And finally, we estimated the maintenance annual costs to be around $800 for the pond and the pump. Now, as for the life cycle analysis we have conducted for this project, we assessed the project for the manufacturing, the transportation, the use, as well as the disposal of the products. The 2 items we assessed are the pump as well as the agricultural activities, such as the runoff recycling, the PSM application, as well as the fertilization. After the assessment, we have come to the conclusion that about 1675 kilograms of CO2 will be produced from this design.
Overall, this design provides a fresh and alternative way to promote sustainable farming practices, as regenerative and sustainable farming is the key to ensuring the future of our planet and global food security. The combination of the runoff recycling system and the application of PSMs have the potential to decrease farmers' reliance on rock phosphate-based fertilizers and increase crop yield. Through funding and more testing of the design on a variety of crops and farm sites will help further validate the design's effectiveness and improve its efficiency. VSAF Inc. believes this design has the capability to be easily integrated into many current farm sites and is the key step towards changing the fertilizer and farming industry for the better.
Below are all the links that we utilized in this presentation to obtain all the images, the number for the cost analysis, as well as the life cycle analysis.